Today we're going to switch gears a bit from talking about the DFT and the FFT and filters, and we're going to talk about using data, for example, from the DFT or FFT or other things to do classification or pattern recognition or clustering and so forth. The basic idea is that we would like to take some signal, say x of n. Now often this signal would be an image, but in this particular case we're going to keep it simple and keep it one-dimensional. Put it into a feature extractor and then throw that into, who knows, say classifier or detector or something else that operates on the features of the signal. So first off, what do I mean by feature extractor? You can think of features as descriptions of the signal, and there are a variety of things that this could include. It may be just the energy, or maybe a short-term energy or power, or perhaps something a lot more complicated, the spectral shape. So the spectral shape may come from, say, the FFT. Other examples could be things like zero crossings, linear prediction coefficients. A popular one is frequency Kepler coefficients. It could be just samples of the signal itself, peak values, on and on and on. There are many things that you could think of, I'm sure, that could be used to describe a particular signal. The variance of the signal, or the variability, whether the signal is constant amplitude or it changes in amplitude. So there's a variety of things that we can use to describe what a particular signal is, and that might work for particular applications. Typically, to accurately describe the characteristics of the signal that matter, we'll have many features that are extracted. For example, with speech, we extract the frequency Kepler coefficients, and we also extract their temporal derivative, how the coefficients change over time, and the temporal second derivative. And we call those the deltas and the delta deltas. When it's all put together, we get something that's almost 40-dimensional. Or something else that just a little bit simpler, if we looked at the short-term energy, maybe we would get the energy every 10 milliseconds or so, and this could trace out what's going on with the waveform. Spectral shape, we may just use the FFT, in which case maybe the spectral shape will be 64 dimensions, and we have a new spectral shape every 20 or 40 milliseconds if we're dealing with an audio signal. So we have a lot of different ways to describe this signal. And so let's look at a very simple case that will motivate where we're going next, and that is what happens when we want to classify something. Okay, so we'll just choose this simple example of is my neighbor playing his music loud or is he not? So I want to know, I'm not at home, but I'm going to complain about it anyway, so I set a recorder out and I continually record the sound going on. So what would I extract for that? Well, short-term energy would be a really good thing to extract. So my neighbor's over here with his great big speaker blasting sound at my house and disturbing the dog or whatever it may be. So I'm going to put my little microphone out here and record that and process it to see what I've got. So if I look at the signal I get out of this, it might be something along the lines of just background noise, maybe a car passing by, and then my neighbor playing his loud music because he's tired of being stuck inside for COVID-19, and he figures this is probably the best way of keeping people away anyway. So he plays his music occasionally really loud. So if I come in here and divide this into little sections and plot the energy, I would get something that's very, very small, goes up a little bit, and then jumps up, and then down because he had a phone call. Now it's back up again, and there I go. So if I want to determine whether or not my neighbor was playing his music loud, I can just write some little program that comes in and says, anytime we're above that threshold, he's playing his music too loud. So that's easy enough to spot, and right there his music is too loud. That's an easy feature. If we were to plot, I'm going to draw this in a different way. If we were to plot this feature just along the x-axis in terms of the energy, I would get a lot of small values. So I'm going to plot each value here as just, actually I'll plot it a little bit above the axis so you can see it, a dot. So I have a lot of them down at low energy, a few kind of in between, maybe when the car passes, and then we have a lot up here at a high energy. So it's really easy to look at this and say, I see a difference. Maybe right here or right there would be a good dividing line. So this would correspond with my line right there. And this line would say, that's my threshold to determine if it's loud music or not loud music. Well, maybe I don't know much about my system to begin with. I just got some cheap little microphone. I don't know how well it works. So I record a bunch of samples and I make a plot like this. And then I can decide later what my threshold will be, because I have this group with loud music up here, and it's really obvious to me where the threshold would be. So this would be extracting the features and then clustering the features, and here I've clustered them into two groups, loud music and not loud music, and then I find a dividing line between those groups, and now I know what it would be. I remember doing something like this early on when I first learned some signal processing and thought I'm going to make a detector for speech, but found that sometimes the dividing line between speech and non-speech, or in this example, loud music and not loud music, isn't quite as clear-cut. But we'll deal with that in a few minutes. The next thing we want to discuss is what happens if I go to something more elaborate than just energy, with more dimensions. So maybe we look at two things. We look at the energy and also the pitchiness. Another word would be tonality. In other words, we want to know, is there a strong pitch or frequency to this? And if it's background noise, the answer would be no. There's just not. But if we had music, presumably it'll have some sort of a pitch. And so we would expect our music to be over here, high energy with pitch. So we measure those two examples and we get over there. Noise we expect to be low energy and not a strong pitch. In other words, no prominent peaks in the frequency domain. And so now this gets a lot easier, because maybe the car comes by and it gives us something down here that's comparable in energy to what the loud music was. But because I added another dimension, it's now what we call separable. I could draw a simple line between there and it cuts everything out. So let me label this. This would be passing car. And this would be just background noise. Or this would be our loud music. Okay, so that was really nice. Now where the car might have overlapped with the music, adding this other dimension helps.